right, so that was matrix inversion. The next thing we can do is what you call Gauss-Seidel iteration or successive substitution. And the idea here is that in the matrix decomposition approach, we have to get these coefficients on each term. And then we put that in the matrix and we invert it. Gauss-Seidel actually doesn't require that you do that. Gauss-Seidel, the basic ideas, here I'll just kind of write out or sketch out the process. So the basic process is as follows. Come here. One, we're going to solve explicitly for t at each node. Right? And I'll show you what that means, but basically we have to come up with an equation that assigns T1 or assigns Ti or Tn. So we have to solve in some way explicitly for each temperature. Two, we then provide an initial guess. So we guess the temperatures at each node. Okay, not unlike ease, where you're providing ease with initial guess values. It could be roughly ballpark close. It doesn't have to be exact. We have to have something to start with. Okay, then three, we compute the new temperature. Compute new temperatures at each node. Okay, using our equations that we derived in step one. Okay, so new temperatures at each node, and then we check error at each iteration. Okay, what do I mean check error? I'm saying we're going through this process of guessing temperatures, recalculating the temperatures based on the equations, and then continuing sort of in that process until we have little enough difference between successive iterations of temperature that we can just terminate the process, right? So we're looking for changes in temperature as a function of iteration. And then when we satisfy that, we're done. So it's kind of this, it's actually a really interesting procedure because you're guessing something, you're just using the internal calculations to reset this value, and somehow you magically get to this actual answer. So it's kind of a cool process. But okay, the process looks like this. So step one, you got to solve explicitly for temperature at each node. Well, that just means, right, I've already kind of solved out for the groupings here. We could go back, we could go back here. We could look at our Maple code, and we could say, all right, T1 is, I'm going to solve my N1 equation, my node 1 equation for T1, right? And I get back my T1, right? Just as simple as that. Or you can, looking at this, looking over here, right? Looking at this, it's just take everything and divide it out by what's multiplying by T1. Okay, so just write out one example and not do the rest, but T1 here would be what? So we are dividing by negative, so we'll cancel out the negative. We're going to have AC TH over R double prime C plus rho E times delta X over 2AC I squared plus what? K AC over delta X times T2. And all that divided by what was multiplying T1, which is just K AC over delta X plus AC over R double prime C. Okay, so we're solving explicitly here for T1. Right? This is the only confusing part, I think. We're solving explicitly for T1, but on the right-hand side, we have other temperatures that we don't know. Right? There's T2 appears here. If we did node I, we would have both temperatures I minus 1 and I plus 1 appearing there as well. But the point is we just need a way to recompute T1 in terms of other things, even if we don't know them yet, right? And so we start off by guessing all the temperatures so we can use them in the calculations. But ultimately, we just need an expression for the temperature that corresponds with the node that gave us this energy balance. Okay, so we can do this for all of the three equations. Right? I won't write it out, but you'd have now Ti is equal to some function, and that function would include Ti minus 1, and Ti plus 1. Right, again, we don't know what those are yet. And then for Tn, we would have the same thing. It would be some function, and then Tn minus 1 would also appear. Right. So, okay, we solved for that. Again, we could use Maple to do that if we wanted to, and then copy it over. But then we can implement this in MATLAB. Okay, so let's take a look at what that looks like. Okay, so here we are. And as a reminder, all these are in the files folder if you want to take a look at them later, use them as a reference. Okay, so we start by clearing. Here's our geometry again. Everything's the same. We set up our distribution of nodes, 101 for this example. And then here's where it becomes different. So it's a little hard to see, but we're saying T old. We're going to have two kind of temperature sets of temperatures that we're tracking. One we'll call T old, one we'll call T new. So we start with T old as a guess. So we could guess really anything we wanted. It just kind of should be ballpark reasonable. And so we know that for this problem, the current lead is going from 300 down to 40. So we could start all of our guesses and just say T old is equal to 300 times the right size. So every single entry is 300. That's what we're doing here. And usually that's good enough, like, to get started. Okay, so we start by guessing a solution. We assign this new temperature that we're calculating first to be our guess. Okay, and then we are going to come in and recompute error for every single time we're doing this. And then once the error falls below a tolerance that we specify, then we're okay. We can terminate the loop. Right. So we initialize our error to be bigger than our tolerance, so we don't fail right away. And then here we come in. So first thing we're doing is I'm going to recompute the new node 1 temperature based on stuff that I'm assuming already. So that for this solution included a T2, right, times a bunch of constant stuff, our generation term, and then the stuff that was multiplying T1 here. Right, so think about what's happening. We're computing a new temperature for node 1 based on something that we just guessed and assigned previously. So T new is just our initial guess, right? Okay, then we do the same thing for nodes 2 through n minus 1. We compute a new temperature, T new I, in terms of the stuff that we've just guessed. If we happen to have computed a new temperature for the temperature that we're using over here, great, we can use it. We can use it right away. And you see that here, like T new 1 for I equals 2 is going to be T new 1 here, right? So this temperature is going to be used directly right here. And in every subsequent iteration or loop through I, this is going to be the thing we just calculated. T old was not computed already. So we're going to use the initial guess that we had from before. So you'll have to kind of stop and think about where we're using T old and T new and convince yourself why we're doing that. But basically we're using a guess, computing new temperatures, getting to the end of the iteration, checking the error between those two things, and then deciding whether or not to do this again. Right. Okay, so then how do we compute error? All right, there's a bunch of different ways to compute error. One way would be, let's say you care about the average error being small. Okay, so you'd do some, root some squared of all the terms and take the square root of that. That's a legit way to do it. Maybe you care about your solution being accurate over the entire span. You don't want any location to have high error. This is one way to deal with that. Then we take the maximum of the absolute value of the difference in the temperatures, right? And that gives us back the worst case error in the whole solution. And if that's better than our tolerance, great, then we're set. So this is just one simple way of doing it. Note that, okay, it's telling me there's a problem, but the problem is I didn't terminate with a semicolon. So if you don't terminate with a semicolon, it's fine, it'll still evaluate it, but it prints that out as you're going. So purposely, I'm not doing that here so we can watch how the error decays. Okay, really important step, last thing within the loop. Once you've computed the new temperatures, you're gonna keep track of the old temperature or kind of reset your guesses, right? You're updating your guesses from your new to the old, or old to new, right? Okay, so you can run this and we can plot it. And let's see, we do that. Again, hiding, it's the same solution, right? And it solved really quickly, indiscernibly different. We can look at how the error progressed, right? So it's printing out the error. Let's see. Right. So it took a few iterations, right? It took a little while to figure it out, but once they got down to a certain point, we said that's good enough, and we're able to move on. Okay, any questions on Gauss-Seidel? Again, it's easy to look at it, and it makes sense, I think, when we're talking about it. When you're actually implementing it, it's a little hard to keep track of where is it a new temperature versus an old temperature. But I think doing examples and going through it yourself is probably the best way to do it. And again, this is the one you want to use if you're programming a solution in Python or something where matrix inversion isn't readily available. Okay.